Hi everybody, welcome back. Today we're going to be looking at the comparison test. Alright, we're still in the section of sequences and series, and we want to develop more methods to determine whether a series is going to converge or if it's going to diverge. Alright, now on the screen here I have that I want you all to recall from section 7.8 when we were dealing with improper integrals. That we discussed this comparison theorem for integrals. And in that comparison, we were able to define either a curve that was going to squeeze from either above or below for this integral that we were observing. All right, so we were either looking to bound it from above or bound it from below, depending on whether it converged or diverged. All right, so we want to build upon that. So the question I have here, the first question says, how do we determine if this given series converges or diverges? All right, so that's the question at hand. How do we determine that? Next question, how can we use the series of 1 over the square root of n to answer the previous question? All right, so I'm going to leave that to you all so you all can think about that. All right, now what I'm going to do here is we're going to start talking about the comparison test. Think about the comparison test very, very similar to that squeeze theorem that we learned for sequences, and then the squeeze theorem that we learned back in Calc 1. We want to keep using that. In this particular instance, we're going to be using the comparison test, and this is for series. So we're going to define two series. One of them is going to be a sub n, the other one is going to be b sub n. And we're going to give the following conditions here. That a sub n is going to be less than or equal to b sub n, and this is going to be for all n. Also, both of these values, or both of these functions, must be greater than 0 for what it is that we're going to be observing. Then, if b sub n, so remember b sub n is this function that sits up top, that's bounding up top, so if the series for b sub n converges, then that must mean the series for a sub n must also converge as well. Alright, next, if the series that we found from below, this a sub n, so if this series a sub n diverges, then the series that is bounding from up top must also diverge as well. Alright, so using this comparison test, we're going to be looking to compare different functions. Alright, so we want to build upon this comparison. Now, for the strategies that we're looking at for the comparison test, alright, oftentimes a lot of students tell me that the comparison test is one of the hardest tests to conduct, and simply because it deals a lot with comparing functions. Alright, that means that you need to have this sense of diving into this function and trying to come up with different ways that you can bound this function either from below or from above. Alright, so we want to develop those ways. Alright, secondly, once you figure out how you want to bound this, alright, and I'm going to start writing this down. Strategy/approach. Alright, so number one, we said that we want to figure out how to bound. Alright, so bound the explicit function from above or below. Alright, now there is no straight way answer to say, oh yes, it's always going to be from above, or no, it's always going to be from below. This is actually trial and error. So oftentimes what I do as I'm working through these examples, I'll bound it from both above and below if it's possible. Once I figure that out, I then just start moving through the convergence and divergence for the functions above or the functions below. Typically, that's a good way to kind of help you guys out to identify what should be done. All right. Once we do that, secondly, the functions that make the bounds have to be easily identified as convergent or divergent. Now, what does this mean? Well, this means that whenever we want to build or whenever we want to identify whether a function converges or diverges using the comparison test, then the functions that we found above and below the initial function that we're looking at, we must be able to determine whether that function is going to converge or diverge. Typically, we like to use the p-series, harmonic, or geometric. Or geometric series. So when we're identifying, hey, I think this function might work to bound this from above, or this one might work bounded from below, the next question that you should ask is, can I then identify whether that function that I've selected converges or diverges by using the p-series, harmonic series, or the geometric series? All right. Once we're able to determine that, then the work moves quite easily after that. All right. And again, I put the word easily in quotations, even though you guys can't see me there. So quote unquote easy. So let's go with a few examples. We want to determine whether the series converges or diverges. Part A. We're going to be looking for this series, n is equal to 1, going towards infinity, for n minus 1 divided by n cubed plus 1. All right, so this is a series that we want to then look at. All right, so once we've found this series that we want, once we observe the series that we're given, I'm just going to extract what I'm looking at for my function. All right, so what I'm looking at here is that I'm looking at n minus 1 divided by n cubed plus 1. So I need to somehow, some way bound this function either from below or from above. All right. And again, my goal is to get a p-series, either harmonic series or geometric series. All right. So to look at those series, and I'm going to write those series right here as they are in order here. So I want to see either a p-series, I'm beginning at 1 going towards infinity, and this is going to be n to the power of 1 over n to the power of p. All right, so that's going to be my p series. Or we can have a harmonic series. Remember, harmonic series diverges. All right, or we can have a geometric series. N is equal to 1 to infinity, and this was a times r to the power of n minus 1. All right, so one of these series is what we need to identify. All right, and more importantly, you want to identify the explicit function here. All right, so let's start looking at this function. First of all, this function is a rational function, which is good because again, looking at my concept over here, I have those to be rational functions. The only one that's not a rational function is the last one, which is geometric. So this kind of leads me to believe that I can be using either first or second one. Now, if you might be saying, hey, Mr. Castro, isn't harmonic series the same as p-series? And yeah, it actually is. The harmonic series is just a special case of the p-series. It's when p is equal to 1. If p is equal to 1, then we have the harmonic series. All right, I typically list them separately because the harmonic series, we pay a lot of attention to that. All right, so looking to cancel that third option. All right, so that leaves us only with these two options where I just really want to get this p-series to take place. So what I'm going to do is I'm going to start, quote unquote, peeling back on this function. All right, so I want to build a comparison here. So naturally, what I'm going to do is I'm going to eliminate one of these constants. All right, because if you look at your original series here, up top in green, they don't have plus or minus certain constants. So if we peel back some of these constants, my suggestion is peel them back one at a time. Then we can analyze what is taking place. So if I remove this -1 from the numerator, which one is now larger? Well, the function to the right is now larger. Okay, great. Now, again, I'm going to peel back some more. What would then happen if we peel back another layer, saying that I want to now take away this constant? Well, which one is now larger? From the denominator, we took away 1, which means this denominator, n cubed plus 1, is going to make this fraction smaller than this fraction here, because this does not have a plus 1 in that denominator, which means, again, we hit an inequality. Awesome. Now, again, remember I said I want to peel back the constants. I want to remove the constants one at a time. This is a specific case because check out what happens once we attain this new function. N divided by n cubed, that is 1 over n squared. Now, this here looks like the p-series. So what I'm going to do is I'm going to say, hey, I've now attained your p-series. Awesome. So in this particular case, we got the p-series. Yay. Now, let's check out what's happening. All right. So if we check out what's happening here, well, for the p-series, anything greater than 1 is going to converge. So naturally, now that I found that value being greater than 1, I can then say, hey, this is going to converge. All right. Now, does that help us? Well, we found a function that is bounding up top. That means, as we're looking at this, we found this b sub n, this formula for the top, and that formula right here is going to converge. So what does that tell us about our function that is bounded from below? Well, it tells us that it's also going to converge. So I'm going to explicitly write this really quick. I'm going to say so. We have this n minus 1 and then n cubed plus 1, and that is all less than this function of 1 over n squared. And again, my work is right here. And the series 1 over n squared is convergent by the p-series. Therefore, my series that I was initially looking at, n minus 1 over n cubed plus 1, is convergent by the comparison test. And there we have it. That is how we're using this comparison test, which again, we have to build a comparison. If we build a comparison, then we then have to analyze which series is diverging, which one is converging. All right, so far so good, hopefully. All right, so that was part A. Let's go on to part B. And when you're doing this, what I'm looking for, as I'm grading exams, what I'm looking for is this part here. I label this as number 1. I want to see, can you build a comparison? Number 2, can you tell me how that comparison fits in with the series? Number 3, can you then tell me, with that comparison, that new series that you developed, is it converging or is it diverging? And then finally, I want you to tell me, to answer the question, is the series that I gave you convergent or divergent? And you must tell me why. All right, so these questions are built as a 4-part question. You need to find that comparison. You need to show me that comparison works with series, all right, just by listing it here. Number 3, you need to tell me what your new series does. And number 4, tell me the conclusion of that. All right, so let's look at a next one. This is going to be the series with n beginning at 1 for 6 to the power of n divided by 5 to the power of n minus 1. Okay, so as you're looking at this, you're going to say, okay, hey, that is a rational function, and you're absolutely correct. However, I want your attention to draw to the exponents. Look at those exponents there. Those exponents have the variables embedded in them, opposite of what we had here for part A, all right, or unlike part A, not opposite, unlike. So that means harmonic and p-series are out of the question, which means we must go to the very last option. So let's go to that very last option and let's take a look at what's going to happen there if we have a geometric series. So again, we want to build a comparison. So I start off with the actual function that I am working with. 6 to the power of n divided by 5n minus 1. And again, you want to start removing constants one by one. So my next function is going to be numerator has no constant, so I leave it as is. Denominator does have a constant of 1, so I'm going to remove that. If I remove this constant of 1, which function is now higher? The first function or the second function? Well, it's going to be the second function. The second function is larger, or sorry, my apologies, 5n minus 1. So in here, if we were subtracting 1, this function here is going to be larger than this function here, like such. Awesome. Now, looking at this function here, we now have 6 over 5 to the power of n. Okay, that's not too bad. And at this point in time, we can now see this will give us a geometric series. Yay! Geometric series. Well, is that geometric series going to diverge or is it going to converge? The geometric series, in this case, has a common ratio of 6/5, which is greater than 1. So, this geometric series is diverging. Now, let's look at what's happening here. All right, we bounded this function here from below. So what we did is we looked at the comparison test and we said, hey, our function is now the top function. The new one that we found, that 6 divided by 5 to the power of n, is the lower function. But the lower function diverges. So that lower series now diverges. That means that my top function, the one I'm really concerned about, also diverges. So, looking at this here, I'm now going to start summarizing. All right, so I'm going to say, so my series for n is equal to 1 for 6 to the power of n divided by 5n minus 1 is greater than my series beginning at 1 for this geometric for 6 over 5 to the power of n. All right, not too bad. And the series of 6/5 to the power of n is divergent because it is a geometric series. Oops. A geometric series with r greater than 1. All right, which again tells us that we are divergent. Thus, the series that we're concerned about, n is equal to 1, 6 to the power of n, 5n minus 1, is also divergent by the comparison test. And there we have it. Again, what I did was, number one, I found a comparison. All right, I identified that comparison, so I then said, hey, this is how we're comparing the series. Number three, I looked at, tell me what that new series is doing. Is it divergent? Is it convergent? And then tell me why. All right, it's geometric, greater than 1, a common ratio greater than 1, divergent, or you could tell me it converges because the common ratio is going to be less than 1. All right, however you want to state that. Number 4, I then want to look at, once we have this new series and the outcome for that, well, what does that tell you about the comparison that we built here? All right, so that is how we're working with this. Now, let's look at part C. So for part C, I want here the series for k beginning at 1, and this is going to be for k times sine squared k divided by 1 plus k cubed. All right, nice. So now is when we want to then start identifying, all right, the same things that we were initially looking at. All right, we know we want to build a comparison, all right, and we want to build a comparison using the function that is given to us. So let's go ahead and let's start with that comparison. All right, I'm going to take here k times sine squared of k divided by 1 plus k cubed. And again, remember, I want to start removing these constants. If I can remove constants or if I can find bounds, then I want to do that. All right, so number 1, I can remove this constant. That'll be great. All right, number 2, I need to identify, do I want to wind up with a p series? Do I want to wind up with a p series, a harmonic, or a geometric? Now, looking at part C for this function, none of this screams out to me that it should be a geometric series. All right, and the reason it doesn't scream out to be a geometric series is because the exponents do not have the variables. So that's telling me, hey, this is not a geometric. So I need to get a p series going here, or a harmonic, whichever one. One of the items that we're going to note here, I'm just going to do it right below, note. Sine squared of some angle, call it theta, is bounded between two values. Well, the initial value of sine is bounded between -1 and 1, but what happens when we make -1 squared? It just becomes +1. So if we're squaring and everything is positive, then it's 1. What's the smallest value that sine squared theta can then take on? Well, that's going to be 0. All right, so what we have here is that we actually get from below, we can bound this by 0, because again, sine squared, that's going to be the smallest value. But then we can also bound this from above, and bounding this from above, using this value of 1, we can now do k times this upper bound of 1 divided by 1 plus k cubed. And look at that, that's real nice right there, because now that 1 is very inconsequential now. So what we're going to do is we're going to start peeling back the constant that we're adding in the denominator. So now if I take back that constant, or if I remove that constant from the denominator, check out what we have left. All right, that's not a bad function to be left with. Now, which one's larger, the one on the left or the one on the right? Well, the one on the left, we're adding 1, and the one on the left, we remove that 1, which means larger denominator on the left means smaller fraction. So I have a denominator here, smaller denominator, which means larger fraction, which means this one is larger. But in doing so, look at what we just found. P-series, yay! We found a P-series. And is it going to converge or is it going to diverge? Well, in this case, P-series, where P is equal to 2, this is going to tell me that I converge. And this function is bounding above for this initial function. So that's kind of a good place to be at. All right, so we're now going to go through and we're going to start our write-up here. So I'm going to say my initial function, or my initial series, for k is equal to 1, for k times sine squared of k divided by 1 plus k cubed, is less than my function for k is equal to 1 for 1 over k squared. And this series converges, because it is a P-series with P is equal to 2. Hence, now I'm summarizing. Now that I know that, what does that mean about my original function? 1 plus k cubed. So that now tells me that this series is also convergent by the comparison test. All right, awesome. Now, one quick note. If we would have done all this work to get to this series here, and if we would have then analyzed this series, and for some reason this series that we ended with, the one that we found, if this was divergent, this would tell me nothing about my original series, because this is bounding from above. All right, so if you have a series here, and if you have another series above it, but that series diverges, that tells you nothing about this series. The only time it does tell you something is if the function up top converges. Then that means this bottom function must also converge as well. So be very careful when you're building your comparisons. All right, building your comparisons, you have to build your comparisons in such a way that you're then going to be able to extract, do I have a p-series? If so, what kind of series do I have? And is this above or below? All right, number D, or part D. We're going to have a series with n is equal to 1 for 1 plus cosine of n divided by e to the power of n. All right, again, we're in the business of converging or diverging using comparison. So let's start off with the function given. I'm going to start off with 1 plus cosine of n divided by e to the power of n. Now again, I'm looking at cosine. Anytime I'm looking at cosine and sine, I can automatically go back to trig and figure out what those bounds are. So cosine of some angle measurement is always bounded, meaning its outputs are always between -1 and 1. So naturally what I want to do here is I want to use one of these bounds. Either we can bound this function from below using my lower bound, or we can bound this function from up top using my upper bound. Whichever one you'd like, you're free to use. I am bounding this from up top as such. This then simplifies to be 2 divided by e to the power of n. Now, what kind of series is this? Well, this in here is our old friend geometric series. Again, because the variable is in the exponent. Yay! So, will this then converge or diverge? We have to find out. All right, so we're going to be looking at my geometric series where I'm going to have 2 times 1 over e to the power of n. Now remember, n in this case is the exponent and e is that constant. So we then have to look at, oops, I meant to write that all in green. There we are. So now we're going to say here the common ratio r is just 1 over e. So 1 over e for the common ratio, that is definitely less than 1. All right. So once we're able to build that common ratio to be r less than 1, that's going to tell me that this series converges. All right. So let's take a look. There we are. So this is going to be 1 plus cosine of n, all divided by e to the power of n. And then we built our comparison to say my comparison in this particular case, n is equal to 1, was that 2 over e to the power of n. But that series of 2 times 1 over e to the power of n is a geometric series with r being 1 over e, which is less than 1, thus it is convergent. Therefore, the original series that is in question here for cosine of n divided by e to the power of n and beginning at 1 is also convergent by the comparison test. And there we have it. That's all there is to it. That is how we're using the comparison test. All right. So hopefully that's not too bad. Again, the hardest part that we have to look at is when we're looking and when we're trying to analyze what is a comparison. Notice if I did the comparison from below, I would probably get a similar result. Nope, I would not, because from below, if I were to take that option, this would be 1 plus -1 divided by e to the power of n, and then I would just get 0. Which means from below, I wouldn't be able to do anything because that would be my series, which would just be 0. So, we got to be careful with that. All right, inconclusive there. So, now that we got this comparison test in our toolbox, what we want to do is we want to talk about the limit comparison test. All right, the limit comparison test is used, and it's based off of our work that we did here. We're now going to start interpreting if we can start analyzing a function with another function, then can we put those into a ratio? If we can put them into a ratio and then take the limit as n goes to infinity, then if the numerator converges faster than the denominator, then the overall series will converge. Or if the numerator diverges, well then the other function will diverge as well. All right, so we got a really powerful tool here for the limit comparison test, which will actually bypass, do we want to bound from above or do we want to bound from below? All right, oftentimes it's hard to identify bounding from above or bounding from below. The limit comparison actually allows us to bypass that for above and below and just work with the initial functions that we are finding. All right, so let's write up that limit comparison test. All right, so here's your limit comparison test. All right, we're going to have that suppose a sub n is greater than 0 and b sub n is greater than 0 for all n that are greater than some random integer of our choosing. Number 1, if the limit for the ratio of those two functions is equal to a constant, and that constant is greater than 0, then both of the sequences must either converge or both of them must diverge, which is really, really interesting and hardy to know. Number 2, if the limit of the ratio as n goes to infinity is equal to 0 and the series in the denominator converges, then so must the series in the numerator. Number 3, if the limit as n goes to infinity for the ratio once again is equal to infinity, then, and the series for b sub n diverges. That means in the denominator, if that series you can extract that it diverges, then a sub n, that series, must also diverge. All right, so using this comparison, what I want to do, or this limit comparison, what I want to do now is I want to start on these limits. All right, so we're going to go through and we're going to start on the limits, and we're going to use a few examples here. So I'm going to say this first example, determine whether this series converges or diverges. Part A. We're looking at the series where n is equal to 1, and this is going to be for 2 divided by the square root of n plus 2. All right, so let's start by looking at this particular series. All right, now I'm going to identify that because I have this series, one of my functions here is that function of 2 divided by the square root of n plus 2. So what I'm going to do really quickly is I'm just going to identify my a sub n as 2 divided by the square root of n plus 2. Now my denominator. Now the reason I want my denominator, I want to identify my denominator, is because that's what's going to do my comparison. Alright, so I want to extract a denominator that will make this comparison, when I insert this into my limit, very viable to determine whether it's going to converge or diverge rather, quote unquote, easily or not. What I want to choose here is just going to be the function, and I'm going to scale back all of these constants of 1 over n. Why am I choosing this? Because it's going to be a p-series. Well, what do I know about this p-series? Well, that's going to be p is equal to 1/2, and then all I need to determine is, well, p is equal to 1/2. Is it going to converge or diverge? Well, if the p-series has smaller exponents, it's then going to diverge. So I'm going to say diverge. All right, so I'm going to hold that in my back pocket. Now what I'm going to go do is I'm going to start with this limit comparison. I'm going to take the limit as n goes towards infinity, and I'm going to take this a sub n divided by my b sub n. So let's look at what that looks like now. A sub n is this function 2 divided by the square root of n plus 2. And then all of that's going to be divided by 1 divided by the square root of n. Alright, I have a complex fraction, so what I'm going to do is I'm going to eliminate that complex fraction by multiplying by the square root of n, both numerator and denominator. In doing so, I get a new function, the limit as n goes to infinity. Now multiplying this in here, actually, yeah, that'll work out quite nice. The denominator here is just going to be 1. Numerator is going to be 2 square root of n divided by square root of n plus 2. Alright, doesn't look too bad at this point in time. Alright, it looks a little bit more easier on the eyes. Alright, now what I'm going to do at this point in time is we could use L'Hopital's rule. That would be okay. All right, that would be one option. A different option is to then divide by that 1 over n, and it will then leave us with the limit as n goes to infinity for 2 divided by 1 plus 2 over the square root of n. All right, not too bad here. All right, which now means that this limit, well, this is going to go to 0, so that's going to leave us with a limit of 2. Nice. This is that constant value that we were looking at for case number 1. Look at case number 1. It says that if you take the ratio of if you take the limit as n goes to infinity for the ratio of the two functions, and if it's equal to a constant, where the constant is greater than 0, well, that's equal to a constant that is greater than 0. Yes, awesome. Constant greater than 0. Then both of your series are either going to converge or both diverge. Well, we know about one of them. They diverge. Or the denominator at least diverges. The series for that denominator will diverge. That must mean that the numerator must also diverge as well. And the series for the numerator was the one in question. All right, so let me go ahead and let me state what I have. I'm going to say note that the series at n is equal to 1 for 1 over the square root of n diverges because it is a p-series with p being equal to 1/2. So my series, the one that was in question, square root of n plus 2, also diverges by the limit comparison. All right. So again, what I'm doing here, or what I'm going to be grading on, number one, I need to see that you define your functions here. What is a sub n? What is b sub n? Tell me what they are. Number two, can you put them into a limit, and can you extract what that limit will then be? Number three, now that you've extracted that limit, it's either they went to infinity, they went to 0, or they went to a constant that's greater than 0. Once you find that, we can then say, hey, the series that we then chose, that b sub n, is either going to diverge or converge. And because that diverges or converges, then we can say, using the limit comparison test, based off of this result, this will also diverge or converge. All right, so that's what I'm looking for those four things when we're talking about determining whether a series is convergent or it's divergent. All right, let's look at a different one now. Let's look at the series for n is equal to 1 for n squared plus n plus 1 divided by n to the 4th plus n squared. All right, so I'm going to extract this as my a sub n function. All right, so here's my a sub n function. This is going to be n squared plus n plus 1, all divided by n to the 4th plus n squared. All right, great. So now that I have this, I need to find a b sub n. So remember, we ultimately are basing this off of some comparison. We don't just want to build some b sub n just pulled out of thin air, right? We want a b sub n that will be somewhat comparable to the function that is at hand. So notice, if I scale back the constant here, I don't have anything that's too beneficial, so that's kind of out of the question. Or it's on the right track, actually. But what I want to do is I just want to look at the two leading coefficients. So let's look at the two just leading coefficients as such. Or not leading coefficients, leading terms. Looking at the two leading terms, this actually builds a good comparison for us. That comparison is going to be that we're left with 1 over n squared. And again, because if we build an inequality, we can still find that comparison as an inequality that this will still satisfy. And more specifically, this function here is a part of a p-series. Yay. And this here is going to be p is equal to 2. Remember, higher p's means that the series will converge. Awesome. So now that we have that, again, that's just in our back pocket. What I want to do then is I want to start looking at these limits then. So let's look at the limit as n goes towards infinity for a sub n divided by b sub n. All right, and we're going to go through and we're going to type in a sub n, which is n squared plus n plus 1 divided by n to the 4th plus n squared, all divided by 1 over n squared. There we are. All right, so let's go ahead and let's clean this up just a little bit more as n goes towards infinity. All right, and this is going to be just n squared plus n plus 1 divided by n to the 4th plus n squared, multiplied. So again, if I'm dividing, I multiply by the reciprocal, and that's multiplied by n squared over 1. All right, so not looking too bad. Limit as n goes towards infinity, and this is going to be for n to the 4th plus n cubed plus n squared, all divided by n to the 4th plus n squared. Now, you are completely right. We could have canceled one of these factors out. If we would have canceled one of the factors out, we're left with something still equally good. I'm going to factor out an n squared from that numerator, so a numerator is going to cancel with one of the n squareds in that denominator. So when I factor out my n squared from my numerator, and I cancel out with the denominator, I'm just left with n squared plus 1 in that denominator. Now, in this particular case, what I'm going to do is I'm going to divide both numerator and denominator by n squared. In doing so, we're now left with 1 plus 1 over n plus 1 over n squared divided by 1 plus 1 over n squared. Now, as we take the limit here, as n goes towards infinity, these terms all go to 0, which means my limit here should just be 1. Awesome. So the limit is 1, and again, this is the constant that we're looking at that needs to be greater than 0. Awesome. That's great. So now that we have this, all right, that's awesome, because now they both, these limits actually got us to a constant that's greater than 0. So that now tells me by the limit comparison, by property number 1, that both of the series are either going to converge or diverge. And that's really nice because I've already dissected this piece here. So let's go ahead and let's say what we know about this piece. And that's b sub n is convergent because it is a p-series with p being equal to 2. Thus, the series at hand converges by the limit comparison test. There you are. And again, this is how we are working with these specific functions. Instead of finding a comparison, we actually just use the limit and then use the result of that limit as n tends to infinity to figure out how we're going to be able to find this. All right, to determine is it going to converge or is it going to diverge? Well, there you have it. All right, so I hope that you all enjoyed this lesson, and I will see you all for the next one. Have a good day.